So this is my second talk for the day on this course. This time we're discussing the very basics of imaging. So what should you do with different kinds of microscopes to make sure that your data is as good as possible. And now that we understand what an image actually is, we can start thinking how this image come to be, and more precisely we will discuss what is the signal we are measuring it. And I ask you to remember that we are not discussing how we take pictures, we are discussing how we are doing measurements, how do we record data. And of course the signal itself depends on what we are measuring, but as we are discussing light microscopy, our raw signal is inevitably photons. As you might know, the fluorescence works roughly like this. So first we have a higher energy photon coming to an atom, and it hits an electron and bumps it to a higher state, and then it hangs out there for a while, and then it eventually drops down to a lower state and emits a photon that has a lower energy. So that's why we see the color shift from blue to a green. But this is not how it actually works. The reality is more complex, as you can see here. So the excitation kicks the electron to one of these sub shells, or these virtual states, where it can hang on for a while, sometimes dropping down a bit before it comes down all the way. And then we have also a kind of dark states where the electron can end up hanging out for a while, and this is one of the reasons why we lose some of the excitation light. And that is just the excitation point. Additionally, some other things can happen to a photon before it reaches your sample or comes back to your detector. So there's a problem called refraction. So light has a nasty tendency to bounce off from hard stuff it hits. So instead of exciting an electron, your photon might hit one and bounce off. And this scattered light might end up where we want it to go, or it might not. And additionally, the light might be absorbed by your sample, and so the photons are lost on the way to the sample, and they are lost on the way from the sample. And both of these effects happen more often the longer the photon has to travel through the sample. So the thicker your sample is, the fewer photons are going to reach your sample, and the fewer photons are going to come out. Modalities. In this talk, we will focus on the two modalities bioscientists are most likely to encounter in the laboratory, but of course, there are many other kinds of microscopes as well. First, we will walk through how wide field microscopes work, and then we'll take a look at the confocal microscopes. Wide field microscope acquires an image of entire field at once by bathing your sample in light. This is often very simple and robust. So basically, we have some kind of a light source which sends out white light, and then we have excitation filter which will filter out the light we want, blue in this case. The blue light goes through the objective and into the sample. Then in the sample, some of the excitation hits your fluorophores, some of it gets lost. Then we get emission. Some of the emission gets lost, but some of the emission comes back through the objective, then through the dichroic mirror, and then finally through the emission filter, which will hopefully filter out all the light we don't want, and the light which we deem acceptable will hit the camera, and that's the image we record. And the longer we put in light, the longer exposure time we have, the more signal we will get. The wide field microscopes are quick and effective because in effect they bathe your sample in light. Everything in the field of view will be excited. Everything in focus, everything out of focus, even if of course the stuff out of focus will be excited less than the stuff in focus. So we have light coming into the sample, and then light going through the sample, and everything in the sample will be hit by the light. This means that you don't want to imaging anything that has more than a single layer of cells if you can help it, even if the autofocus light will give you less signal than the in-focus light. If you have lots and lots of stuff in the autofocus area, you will get also lots and lots of signal from there. Wide field microscopes can be pretty damn fast, and with a good diode stain, we can use pretty short exposure times, which allow really fast imaging, which can be really convenient if we need to look at quick events or if we need to image a large area. They are pretty easy to use. You just point at what you want to see, and you set the exposure time, you choose the filters, and you're good to go. The problem is that they have a really poor depth resolution, as discussed before, and while you can take a stack and deconvolve the stack, confocal images are almost always better in this case. As you know, the wide field microscope uses a camera to record your images. The camera chip consists of millions of photodiodes, like this. The incoming photon is used to excite electrons here, and these electrons are then collected in storage and afterwards transferred to an amplifier. Most notably, this process is almost linear, so if the concentration of your fluorophores in the sample doubles, the signal we read out also doubles. Next, we will discuss the most important imaging parameters of the wide field imaging. So first we have exposure time, which basically tells you of how long you put light into the sample. The more light you put in the sample, the better images you will get, as long as you are not overexposing or burning your sample. Then we have optical magnification, which is just a fancy way to say which objective you are using. So objectives and possible magnifying lenses determine your pixel size, and of course your pixel size affects your signal and your resolution. And additionally, most microscopes offer you a possibility to do something called binning, which can be used to gain more signal at the cost of resolution. And we'll take a look at this binning thing next. Binning means that we combine pixels so that intensity values become higher, but we end up with fewer pixels. This has fringe uses when the sample is dim or we want to acquire images really quickly. So imagine we have an image like this here, and now we become to bin it. So assuming we are applying 2x2 binning, we would take this 2x2 space and sum it together. So this would be 0 plus 10 plus 0 plus 10 is 20. So this becomes a new pixel here. Similarly, this 2x2 space, so we would have 20 plus 20 plus 20 plus 40, so this becomes 100, and this becomes pixel here. And then this process is repeated all over the picture. So let's have a look how this binning first. We are going to bin Fabio, and then we're going to bin some cells. So as you can see with Fabio, we only really lose resolution. So the Fabio was here to show you just how much resolution you can lose when you use binning, and then the cells here are to show you how much signal you can gain by doing this thing. So basically this is a last crutch method that you should use only when your signal is so poor that nothing else helps. As I said, you only really need binning if your signal is really poor or if you're working with a stain that disappears when you look at it. If you find yourself in a situation, the first thing you should do is to optimize your protocols or get a better label stain. Only and only when this doesn't work out, you should resort to binning. Also, in cases where you need as many pictures as possible, quickly as possible, binning might actually help, but of course you also lose resolution, so that might not actually end up helping you at all. Next, we are going to discuss confocal microscopes. The confocal microscopes are also known as scanning confocal microscopes, and the magic word here is scanning. So assuming we have our sample here, the microscope actually literally scans it with laser. So first the laser will draw one line, and then it will jump and draw another line, and jump and draw a third line, and so on and so on and so on, until we have scanned the whole sample. Then within the line, the laser hovers very briefly above 1 pixel, and meanwhile we collect the light coming from that pixel. Then the laser moves to the next pixel, and again we collect the light coming from that pixel, and so on and so on and so on, and we end up with a map that tells you with how much light we got from each pixel, and this map is in effect your image. The detection scheme for confocal microscopes is much like that for the wide field. So we have a light coming from the laser hitting the dichroic mirror, then it will go through some mirrors which are used to do the scanning part, and through the objective into the sample, and then it's coming back through the dichroic mirror, through filter, and through pinhole to the detector. The confocal microscopes are used to excite a very narrow plane within the sample, and of course, because the light goes through the sample, we will also excite some stuff below and above the sample. But then we have something called pinhole, which is here on the light path, which makes sure that the light that comes out of the focal plane, that is, it doesn't come from the focal plane, will be excluded from the detection, and this allows us to see a very narrow slice of your sample. So as discussed earlier, the wide field microscope illuminates your whole sample, so our effective optical section is very thick. That is to say, we get signal from a large thickness, which means that it's really hard to see if two structures are on top of each other or if they are within each other. With confocal, we don't have this problem because our optical section is thinner. Of course, this means that if we want to scan the whole sample, we have to take a lot of slices, and this takes more time. But this is usually the way with the microscopy. You buy image quality by spending more time with your sample. The signal coming from the confocal microscopes is too weak to be measured with a regular camera device. So basically we have to use something called a photomultiplier tube, or one of its more modern derivatives. The first part of this thing is a photocathode, which basically transforms the incoming photon to an electron with some efficiency. Then this electron is focused into the series of diodes, which will amplify the signal by basically kicking out extra electrons for each electron that hits a diode. And this will cause a cascade, which will cause more electrons to come out after each collision, and hopefully then eventually we will get enough signal to be measured here at the anode. And this rate of amplification in the PMT, in the photomultiplier tube, is controlled by something called voltage dropping resistor. And this voltage dropping resistor is the gain you are adjusting when you work at the microscope. The good thing with the PMTs is that they are really sensitive and they can see really faint signals. The bad thing is that they are not perfectly linear, and what this means we will discuss a bit later. Next, we will discuss some important imaging parameters that are related to confocal microscopes. So first, we have a scanning speed. So basically, the faster you scan your sample, the faster you get the image and the less you bleach your sample. However, the faster you scan, the worse signal you get. Then the next parameter is zoom or format, or maybe more accurately pixel size. So the larger the pixel you have, the more fluorophores you have under 1 pixel, and the better your signal is. However, the larger the pixels you have, the worse is your resolution. And the last thing we will discuss is something called gain and offset. So increased gain increase the signal, as discussed earlier, but increasing the gain also increases the noise. And then we have something called offset that can be used to reduce the noise and the signal if necessary. So scanning speed combined with image format, that is to say the size of the image in pixels, gives a parameter called pixel dwell time. And as the name implies, the pixel dwell times tells you how long the laser usually stays in a single pixel before it moves onward. And these pixel dwell times are usually in the range of microseconds. The longer the laser stays in one place, the better signal we get and the less noise we get. On the other hand, the longer the laser stays in one place, the slower the process is and the more you bleach your sample. So the decision on how slowly or how quickly should you record your data is always a compromise. Offset tells us how low signal we record as zero. This can be used to remove background noise when the background is homogeneous. Gain tells you how much the signal is amplified, and this parameter is not linear even if Leica and Zeiss claims it is. And gain, scanning speed, laser power, and resolution should be adjusted to avoid overexposure, and they should be optimized according to your needs. Offset is used to correct for the background, and poorly adjusted offset adds additional signal to the image. So here we have 1, 2, 3, 4 images taken with different values of offset. So the number 3 image here has 0 offset, and as you can see from the cross section taken from here, we actually have a little bit of homogeneous background. Then when the offset is put to -2 here, the background largely disappears. And if we put the offset to -5, well, the background is still gone, but now our signal starts to go down from what it was at the -2. And if we pump up the offset to +3, we will get more background. So the offset is basically, it reduces the value at every pixel or it increases the value at every pixel. And if you are only quantifying structures or locations, you can usually set up the offset quite haphazardly to something good enough. If you are looking at intensities, you need to be more careful, but if you are working with intensities on a confocal, you unfortunately usually need to evaluate your life choices. I took 4 pictures of the same location using a different gain. So here we have pictures 1, 2, 3, and 4. I was using gains from 600 to 900. And what I did, I measured the average intensity of ROI 1 and average intensity of ROI 2 for each picture. So they are shown here. And then I calculated fraction for these. And as you can see, the fraction changes as a function of the gain. In this range, 800 to 900, the fraction stays pretty much the same. So that's good. However, the implications here are that if you are quantifying intensities on the confocal, which you shouldn't be doing, but if you are still doing it, and if your samples have really huge variety of intensities, then the intensities you measure do not accurately represent the differences in the amount of fluorophores you have in the sample. They show the tendency, but it's not, the fraction is not accurate. Noise or unwanted signal is present in every image. This is not because the microscopes are bad, this is because physics happens. You can reduce the noise almost always, but this improvement comes at a price. The price you pay is time. Either you spend more time to prepare a better sample, or you spend more time measuring your data. post-processing only ever alleviates the problem. It will never solve the problem. So if you have bad data, no amount of image processing is going to solve the problem for you. Averaging is a common method used on confocals to get better pictures. So basically, assume we have one ground truth, and then we record it once, and because the microscope is not perfect, we get the noisy image, and then we record it the second time, we get another noisy image, but it's different from the first noisy image. And then we record the same image the third time, and again we get a noisy image, but it's different from the noisy images 1 and 2. So we take our 3 noisy images and we sum them together and we divide by 3. Wherever the signal is constant, the signal will remain constant. But let's say we are looking at some background point where in the image 1 we get some noise. So we choose a pixel here, and let's say that this pixel here in the image 1 has an intensity of 6, when it should be 0 because it's background. But in the image 2 we don't get the noise because the noise is random, so we add +0. And in image 3 it's also 0 because it was a random noise in the first image. And then we divide this by 3 because we had 3 images. And now in the resulting picture, the pixel where we had the background 6 in one image goes to 2. And this means that any pixel with random noise in it will have that random noise reduced. Averaging is a good tool, and you can always increase the time you use to record the data. And it's an easy solution, but unfortunately sometimes you cannot use it because either you don't have the time or your sample cannot take the load. So here we have the same pictures taken with average 1, 4, 8 and 16. And as you can see, the increased quality is greatest from 1 to 4, and then we start to get smaller and smaller incremental gains when we go to 4 to 8 and 8 to 16. This is because the noise is reduced by the factor of 1 per square n, where the n is the amount of average you're using. So the greatest improvement goes from average 1 to average 2, then from 2 to 3, and the higher the n goes, the smaller your gains will be. Usually the sweet spot for the average is somewhere between 2 and 5, with 3 and 4 being the ones being used most commonly. So many of the tools provided by the Windows are meant for photography and general image manipulation. And if you put your data there and try to have a closer look, instead of seeing what you should see, you see something like this. So what happens is that the software interpolates the pixel values for you to provide you with a smoother image. Of course, this looks nicer, but it has nothing to do with the actual true measurement you took. So be careful with the tools you work with so you don't start to see things that are not really there. If you have to resize your images, it is the last thing you do to them before you attach them into anything. The problem is that resizing works as a smoothing filter. So here on the left we have a genuine picture taken with average 8, and then we have shrunk it, and then we have expanded it, and it does not look anything at all like the picture where it came from. So don't do this. And now few final words to wrap up my talks. You often hear claim that you can increase the image quality after acquisition. This depends a lot on what you mean by quality. Any and all attempts to reduce noise after you have taken the picture will also reduce resolution. The convolution is perhaps an exception to this. Also, any and all attempts to increase resolution will also increase noise. Both noise and signal are defined as sudden change of intensity, which means that coming up with tools that affect one but don't affect the other is basically impossible. When you start a new imaging project where you need to measure something from pictures, it's often a good idea to spend one session taking a lot of pictures with different settings. This allows you to figure how quickly you can record usable data. And this can be especially crucial when you're working with 3D data, so basically when you're working with confocals, because shortening imaging time for single sample, even by a few minutes, could save you hours and hours of time, and this could end up saving your boss or you hundreds and hundreds of euros. And finally, I would like to introduce the concept of worst usable image. So ideally, you do not want to spend any more time at the microscope than you absolutely have to. If you take much better images than you need, of course you can get your results, but you're wasting time and money. And if you need lots and lots of data, this cost might be considerable. Of course, it's better to take bit too good pictures rather than err on the other side and then take pictures you cannot use. But you should also consider what is the worst usable image, what is the quickest image that gives you the information you need. And figuring out this might require some optimization. And if you have lots and lots of samples, this optimization will usually pay itself back really, really quickly. And now I will take your questions and try to answer them.